thus P will be the prime always odd prime here. So if L over Q, a number field, so I just set up a notation, G sub L is just a Galois group. All right. So if we are finite prime, and then I denote GLV is just the local Galois group, okay, the decomposition group. At V, we know this is isomorphic to the Galois group of the local field. All right, and the C inside G sub Q will just some complex conjugate. All right, so in my title, I'm going to talk about something about GO4. So I just give you a very ad hoc definition about GO4, but I will give the general definition a little bit later. So, is that right? Yeah. Okay. So the R here is just the multiplier. All right. So this is the character. Oh, here. Okay. So I'm going to consider a subgroup of GO4. So it's defined like this way. So so the G is in the GO4 QP bar. And it's very easy to see that if R times determinant minus 2, okay, so the image must be the positive one or a negative one. So I just make it positive one. Okay, so the index 2 subgroup. So of course, you want to know, the automorphy of certain Galois representation. The Galois representation I consider is just okay, a continuous representation. Well, so if you consider this character and compose it with rho, oh, this is times, okay, compose it with rho. So this is just a quadratic character, right? So it's a one-to-one corresponding quadratic excitation F over Q. This is quadratic. Okay, so I reserve this F through my tag. It just represent, the field corresponding to this character.
Sorry, could you just recall in degree 4, if you take the orthogonal group given by the unit matrix, is it quasi-split?
The quasi-split.
In other terms, there is no compact factor.
Isn't that the algebraic closure?
Oh, it's the algebraic closure. I'm sorry. Okay.
Oh yeah, so it's just algebraic closure. Yeah. So that doesn't matter here. Okay, so.
Where does the square go in? On top.
Which?
First line.
This one.
Yeah. Do you want the square on the outside?
Minus 2. Yes, minus 2. Think of it.
But there you see it.
Oh, I'm sorry. Yeah, you're right. All right, so that's all my notation. Then this morning, Richard gave a very nice. So let's see, talk about the conjecture. All right, so there's a conjecture of a Fontaine-Mater, or I should plus the long length. Okay, anyway, I'll put it here. So I just recall that. So if the rho and there, so in our special case, if rho is okay, so two conditions. First is irreducible and unramified almost everywhere. And the second is the ROM. At P. Okay, so then the conclusion, the conjecturally, so rho is the automorphic. So the automorphic in my talk is that mean because I only consider for the GO4, so that means the rho comes from pi, the automorphic representation of for the GL for AQ. All right. All right. So because Richard has a very nice explanation what automorphic what a Galois representation attached to the automorphic representation, what the ROM means. So I generally don't talk about what does the condition mean. So I just continue. So unfortunately, so for the remaining of my talk, I'm going to replace this condition in the following. So the crystalline. And the hearted weight of this guy, you can always prove it must be like this. Okay, so for the m and n inside non-negative integers. Okay, you can always assume like this. It's somehow a little bit a shame as the periodic Hauger theorist to assume this condition, but it seems that the life will be easy if you consider this crystalline stuff. All right. Okay.
Is it okay if both m and n are 0?
Yes, I will consider some case of the mn equals 0. Okay. Yeah, I think this conjecture is true. All right. So now let's talk about our results. Okay. Okay. The first one. Okay, so of course I will going to assume the condition 1 and the condition 2. Okay, so the theorem 1. Assume 1 and 2. And I'm going to consider the condition 3. So the eigenvalues of the C. So remember the C will be the complex conjugate. So 1, 1, minus 1, minus 1. And the RC will be always the 1 here. The second condition, so this is a really technical condition. The image of the Galois group is actually factored through the SGO4QP bar, which this is SGO4 that's defined there. So second one is just okay, then rho is automorphic. Okay, so that's the first theorem. So then I go to the second theorem. All right, so now assume 1, 2, 3. So first three conditions, 3 is show up in here. So, and then I need the condition 5 prime. So 5 prime will be corresponding to the condition 5 there. So so assume that right now the mn will be between 0 and p minus 1, but unfortunately I have to assume that 2. So I'll let you know where this condition comes from. So 6, well, so P is ramified on F. So remember this F is come over here, okay? And well, let's say called 7, okay? The residual representation is irreducible. So then the conclusion is that rho is potentially automorphic. So i.e., so there exists some real quadratic, total real field extension such that rho restrict to that Galois group is automorphic. Okay, so that's two theorem. All right, so.
Sorry, can we get a few explanations? So first of all, on the conjecture, okay, a priori, if I have a representation, it's going to have arbitrary Hodge state weights.
Yeah, but in this case, you can prove. So I will show you. This can prove the Hodge state weight must be like this.
In which case, if it has this symmetry?
Yeah, in that case. Okay. I always assume.
You didn't say so. So here, this is because you have the orthogonal symmetry.
Mm-hmm.
For the result, for example, for 5, you assume regularity. Could M?
That's the point. I doesn't.
I'm sorry.
It includes irregular. It includes a condition. Sorry, includes a situation which is not regular.
So, for example, you could take.
Yes, M equals to N. Yeah, this is possible, and or M equal to 0. And
like, let's just suppose you take the Galois representation associated to delta.
And
then you tensor it with an even A5 representation.
I'm not quite sure what is that.
Okay, there's a modular form of weight 12, which is delta, which is you have a two-dimensional representation. And then there are two-dimensional even representations with finite image. And if you tensor them together, they'll be orthogonal. The Hodge state weights will be
0, 0, 0.
Well, 0, 0, 11, 11. And I think all the conditions are satisfied. So you're saying that? Yeah,
I think that's because you tensor. You have a two. Eventually, you actually tensor with the two representation which are GL2, and you know there's a modular in each piece.
So you're going to prove the conjecture for even Galois representations?
No. I have this condition. I can guarantee that my representation is odd.
But an even thing tends to an odd thing.
It won't happen. It won't happen here. That's I have this this condition.
Take something even.
Even times odd will give you these 4 eigenvalues.
Yeah, even tends to odd. If you take something like, if you take something that's odd, and you tensor it with something that's even.
No, it won't show up in this case. I can show that it must be.
Well, there are Galois representations that satisfy all these conditions.
Multiply won't be equal to 1. I don't think so. Yeah, that condition will exactly will have two representation, odd representation. Let's see.
Okay. Yep.
Yeah, so that's I insist to use this condition. That just works through all my talk. All right. So yeah. So now of course, so the very important remark. So I have to compare the theorem phi. I believe theorem phi in the BGGT. Everyone didn't understand what that means, right? No, okay. So there's a recent preprint. I think the first one is Barnett Lamb. Second is Garrity, and this is G and Taylor. So they have a very general result about automorphy of potentially automorphy of a certain Galois representation of GLN. And of course, if you specialize that theorem C to this GO4, well, you compare this, there's a 2 theorem there, actually 3 theorem. So in that theorem, they don't use this condition. Okay, so they only assume this part. And okay, for theorem 1, we unfortunately assume this is a very strong condition, but we also conclude a very strong, well, kind of strong conclusion there. Okay. So here that their assumption is potentially diagonalizable, and but I know that if the representation is not ordinary, probably the known cases is just crystalline with halted in the Fontaine-Lafayette range. So here, this is strong technical condition, but this a little bit better. And I think the most interesting case is that.
A little bit better because you can have M equals N.
Yes, I think I just try to make this point right now. So all the interesting point of our theorem is just you see the case of this case. So this theorem does talking something like that. So I think that makes this the 2 theorem is slightly interesting. Okay.
With this thing you get automorphy rather than potential automorphy.
Yeah, that's the point. Yeah. But here actually I use the theorem from your paper, so it only can be only the potentially automorphic.
Excuse me again, but in this case, automorphic, of course, has not been defined this morning because your representation is singular, so you will use limits of Galois representation.
No, I think this comes from Ramakrishna paper. So in that case, if you have 2 automorphic representation of GL2, you make a certain kind of tensor product, you can always get automorphic representation. So that's the point.
Oh, so this is automatically a tensor product here?
No, I will explain. It's not automatic, but it's not very far from.
I couldn't understand.
I will explain. It's not very far from the tensor product.
In any case, these are not cohomological representations. They are limits.
They're not limits. I don't think it's a limit.
You have a singular Hobbes there, possibly. If M is M.
Okay, so I'm not quite sure about the automorphism. I will explain. So what's going on here? Okay. All right. So now, what time is it? Okay. So let's talk about some application here, and just let me know that where my motivation to study such kind of stuff. So let gamma inside SL 2Z be a non-congruent subgroup. Well, so most time we study in a congruent subgroup, but right now I'm talking about non-congruent subgroup. And then, well, for this one, you can still talking about the modular form, okay, with weight k. And you can talk about, okay, so for the arithmetic for this non-congruent modular form, what you can do. It turns out, so you cannot get a single, representation of a single modular form, but you actually attached the whole space of class form to the representation. Okay, actually this is a compatible family, and the D is just a dimension of the space of the class form. They have a very nice property there because it constructs from it's somehow motivic, and so if K is odd and D equals 2, then we know that rho P, the GQ will be inside SO GO4 QP. All right. All right. So then Now the theorem is that, so assume rho p is absolutely irreducible. So there's a little bit vague, but let's assume that p is very, very large, and k dot dot divide k, and d equals to 2. And then finally, let's make a very strong assumption, assume that so the conclusion then, rho p is automorphic. All right, so in general, of course, this condition is very bad. It's hard to know where is such kind of condition is certified. So, but we have a corollary. So if you pose some certain kind of symmetry on the Galois representation, then you can guarantee this thing happens. So if rho p has some real multiplication, by some e over q, that's the real quadratic. So then rho p is automorphic. So the point that if you have such kind of thing that if you somehow you can show that this is actually inside there. So the Vanilli and Ling Long found a lot examples certify such kind of concrete example like this. Okay, so let me say something about why do we.
Is it possible to say simply why the image is in the orthogonal group?
Why?
For these representations Scholl looked at.
Yes.
Why is the image in the orthogonal group?
Oh, it's the orthogonal group because in that case they have a natural pairing, symmetric bilinear pairing to make this thing happen.
Symmetric for some reason.
Yeah, it's symmetric because the k is odd. It's a totally construct from a k is odd. Yeah, yeah. But in the even cases, you will be in the GSP. So in that case, I don't know nothing about that. So let's say something about why do we care about such kind of thing. And okay, so why we study such kind of non-congruous subgroup. So of course, the first answer is why not. Okay, okay. So don't blame me. I learned this universal answer from Chris. Okay, so when I was a graduate student in Michigan. So okay. Second, well, it's actually interesting to see that you see that well, you have a modular form of non-congruous subgroup and you have a modular form of congruent subgroup. How you distinguish between them? Okay, so it turns out it's so-called unbounded denominator conjecture, which see that well, a modular form comes from a non-congruous subgroup if and only if the Fourier coefficient has a non-bounded denominator. The denominator will be larger, larger, and larger. Well, but does anything to do the Galois representation? Well, the Galois representation here is not very close to the Fourier coefficient, but they have some relation. For example, they have some congruence relation. It turns out if you can see something about the automorphy about this representation, then you can see something about this conjecture I have just mentioned. For example, if d equals to 1 here, okay, so it turns out Ling Long and Vanilli can prove this unbounded denominator by the modularity of the GL2. Okay, so so. If it's unbounded, it must come from a modular form of the non-congruent subgroup. Okay. All right. So that's the motivation actually for the case of that case 0, 0, MM. Okay. For that case, I don't have much motivation. I just after talk with Richard, I suddenly realized probably I can even do that case. It's just somehow very interesting. All right, so now Now let's talk about the steps to prove such kind of stuff. Okay, so strategy. So the step one. So it turns out if you restrict to the GF, which is so once again F is there, you can always return the tensor product of these two guys. Well, each rho I is just you can return the tensor product well there. Okay, so that's first step. Now step two. All right, so you return the representation as a tensor product, then what? So you have to certify that's ramified almost everywhere. So that you have to do the odd. You have to do the crystalline. So at V divided P. All right, so you at least you have to prove that. So to prove the modularity. So by the way, I try to eliminate this condition, but I don't by your recent result, but I can't do that. So. All right, so that's step three. That for the GL2, we know a lot about modularity lifting theorem. So. So ALT means modularity, automorphic lifting theorem. Okay. So finally, okay. So you show the individual pieces are modular. Then what? And then by tensor product, so then, so now, so by theorem of this Ramakrishna, okay, so that's the theorem of that if rho I, the GF go to the GL2 QB bar are automorphic, then the tensor product. Okay, so that is the annals paper of Ramakrishna in 2000. So pretty much, of course, they use the language automorphic form. Pretty much, if you automorphic form of GL2, you can cook up some kind of tensor just corresponding to the tensor product of Galois representation side, and he can prove this will be automorphic. All right, so that's use this. So then.
Probably worth pointing out that the converse. Where the source of automorphy is the converse.
Okay. Okay, so, all right, so now I will go over this 3 steps for the remaining of the time. And so let's see first, so which time? 3, number 4, okay. So let's talk about the step 1. All right, so let's see. So namely how I write this representations to the tensor product. Okay, so you see that suppose V is the GQ bar representation. Sorry for that vector space of dimension 4. All right, and then suppose the B, we go to the V to the QP bar is some bilinear symmetric non-degenerate Okay, so if suppose you have this true data, it turns out you can define GO for V and B and the following. All right, so this is G and you got a B, G, V, G, W is just RG and B, V, W, V, W beside V. Just a very standard definition. Okay, no problem. And well, so that's the indicator for a very special situation for the GL2 is that GL2 you can think as the GSP2, and this is a group of similitude. Okay, where this the pairing is the alternating pairing. So for example, any alternating will do the job. Alternating form will do the job. For example, if you can do concretely like that. So for the V and the W, it's just okay. So that's a very concrete that you can think about it like that. So now let's see. I set V is just QP2 tensor with the QP2. Okay, so I get a 4-dimensional space with just by tensor product, and let's define B U1 tensor V1, U2 tensor V2. It's just defined as U1, U2 times Y1 and V2. Okay, and it's straightforward to check. This is a symmetric, bilinear, and non-degenerate form. Okay, so in particular, you see that you get so GL2 QP bar cross GL2 QP bar to the GO4 V and B. Well, so the V and the B is just what I defined right now. And simply, it's just from A here and the B here. You just go to the tensor product. Okay? And there, well, this obviously have the kernel here. The kernel is just QP cross. Well, if any x here, so this x is just go to the x identity times x inverse. Sorry, identity matrix. Like this, you get the kernel. Okay, so just call this map is a Q here. So the fact is that so the Q of GL2 cross GL2 is just equals to SGO4. Okay, so it's just one can prove that. So remember, SGO4 is defined like this. Okay. Okay, so now recall that. Okay, so F is the quadratic field. If you composite multiplier times determinant minus 2 and composite with the Galois representation, you get a character, and you get a quadratic field. So by this way, if you have such kind of relation, you can see that if you restrict to the Galois group of the F, well, this is go to the SGO for QP bar, and then by this relation is projected by GL2 QP bar cross GL2 QP bar, and well, you have a kernel there. All right. So then if you restrict to the Galois representation of each component, so there exists rho I tilde from GF to the, well, not GL2, the PGL2, such that rho isomorphic to all right. Well, you finally get the representation, but it's not the traditional Galois representation, but into the PGL2. So then you have to lift this representation. Okay. Okay, so there, it turns out there exists, you can always lift the representation. So this will be rho tilde, so this will be rho I, and this will be that's a projection map such that okay, so when you lift the projective representation, so first thing in your mind is, okay, so if you consider the exact sequence, so certainly if GF QP cross is 0, then you will complete, the lift. But in general, we don't know this is true. All right, so then, but you can still lift, so we are lift by variation of the Tate theorem. So which is just H2 GF C cross equal to 0. Okay, so you can still do that, but it does not use that fact, but use the traditional Tate theorem. Okay, so then complete the first step. All right, so right now you have this two Galois representation tensor altogether. Okay. So then, then the step 2, you have to show this Galois representation certify the nice property such that you can apply the modularity lifting theorem for the GL2, right? All right, so the problem is that that Galois representation is a construct from the theorem of the cohomology. It's abstractly construct. You know that such kind of lift exists. Then you really don't know nothing about that except that the representation can be proved from can show that it is continuous. Okay, so you first of all, you have to show that rho I is unramified everywhere, almost everywhere. So this is not a trivial statement, but it's not so hard. So actually, if you sit down and work for like 20 minutes, so you can work that. So not so hard. Then is rho I or odd. So that's the point. That's the point that R equals to from the construction. So this must be, both of them must be odd. Otherwise, the eigenvalue cannot be 1, 1, minus 1, minus 1. Okay? And from here, you have another product, byproduct is F is the real. So that's a quadratic extension is actually real quadratic extension. All right, so what else? So now finally, so is that true that rho I is the crystalline? Because you know that rho is the crystalline. Well, generally it's not true because you see the rho 1, rho 2 is rho. Well, rho I itself is different by twist of the character, right? So if you twist by a character which is not hot Tate, then the rho I cannot be crystalline. So the correct formulation for this question is that up to twist a character. So namely, so can we find that the rho 1 twist chi and the rho 2 twist chi inverse are crystalline? Okay, so that's it turns out the most technical part of such kind of thing. Okay, so assume that we have in a local case of course, you can ask this question purely locally. So suppose I have two crystalline representation, local representation. Okay, sorry. Suppose I have two representation of a local Galois group. I tensor together. They are crystalline, the RAM or whatever. So can you up to twist a character? You can see that the two representation are crystalline or have your nice property. So this is the theorem of so it's a complete answer to this question. So let K or QP be finite. Okay, so well, VI is just a local Galois group. Okay, so if V1 tensor V2 are crystalline, then there exists a character chi such that V1 tensor chi and one. Okay, so the story that in order to prove that modularity theorem of this, I've been thinking about this question, but only success for some special cases. Later on, that the Liang Xiao in the Chicago have some idea to prove the general case, but it turned out we found this is actually a thesis topic of a student of Laurent Bourget. So he should claim all the credit for that. Okay. All right. So in that case, if I time allowed, I talk about this idea how to do that. Okay. So here, so if F equals to Q, so that case equivalent to say that the representation, the image of the representation is inside SGO4. Okay. Then you see that so such chi in this statement always exists because the local character, okay, so in that case you can always extend it to a local character, a local character you can always extend it to a global character. That's not a problem, so that's okay. So so remember that we have a situation that F is the real quadratic. Then there will be a problem because a local character in general you cannot lift to a global character. In particular, the situation is that so in the local character you can arrange the weight as arbitrary as you want. But for the global character you have no way to do that. For the totally real field you only have one character, you have one weight there. So that's the problem. All right, so that's the kind of a totally different question. So, but anyway, so it turns out if F not equal to Q, and unfortunately, I can only solve the condition.
I mean, you can certainly. Yeah, go. Sorry. I know what you mean.
So okay. So if only under this condition, then does there exists chi, the row 1 twisted chi and the row 2 twisted chi inverse are crystalline. By the way, from this local theorem, you can always remember that I told you the halted width is always look like that. So that's from this actually come from that local result. All right, so okay, so finally, so okay, so then step 3. Okay, so then your representation for each pieces of representation is already GL2, and you finally can show the representation is odd, is ramified, is crystalline. Okay, then you can use the classical result of for the GL2. Okay, so probably I just mentioned one of that theorem. So if you have a row star from GQ to the GL2 QP bar, if such that the first condition irreducible or almost unramified, so the second condition is odd. The third condition, so the crystalline, that's that. Okay, so let's see the halted width. So then, so the good thing about this theorem, although we assume crystalline and we assume that the crystalline and this halted width has a special shape. But the only a very important advantage, I don't have to worry about the shape of the residual representation. So that combine this theorem, and you actually know that the theorem 1.
Bigger than 0 here? This theorem?
R can be 0 there.
I don't know how big this dual phase data applies to, but there's the result of Buzzard and Taylor in the case when the Hodge state weights are both 0, but there's some kind of extra conditions there too.
I think in this situation, if I remember correctly, the case in the totally, in his review paper, I did say that as a result, because for the Artin conjecture, it can be solved in this case.
Yeah, but you don't know that it's an Artin. I mean, the Artin conjecture is known by Kari, Banter, and Berger, but you're not, if in the case R equals 0, you're not assuming that the row star has finite image, but simply that the Hodge-Tate numbers are 0, 0.
That if you assume crystalline, you don't know about that? I think you do know.
Buzzard-Taylor, for example.
Well, under some hypotheses, yes. Probably you could weaken the hypotheses, but I don't think something as strong as that is in the literature.
Okay, so if that case, I certainly should. I should have to double check that.
What we wrote, for instance, was in the ordinary case.
Okay. Okay, sorry about that. Okay, so double check about that. Okay, so all right, so then I still need to use the very recent theorem of the BGGT I just mentioned about to cook up the second theorem about the potentially automorphic, but that will be okay. So let's that will be easy. It's a similar strategy. Okay, so finally, I just talk something about the step 2. Okay, so let's see something about that theorem. So the idea is that, so if you get any representation, okay, so that there will be exist a chi such that V twist chi is a hot tit. And then by Fontaine, so is well, so the whole point actually, if you know one of the hot tit width is an integer, then in the condition that because you have a tensor product, you can know that all hot tit width of the two representations are integers. So and you can know the hot tit width is semi-simple in that case, and this will be hot tit. And then by a theorem of Fontaine, well, pretty much, well, roughly speaking, if you can show the lattice of, well, you have to show that certain kind of lattice in the realm, well, quotient by some t there. Okay, so if all the lattices have a hot tit, then you can show that this is the realm. Okay, so from the realm, we know that it's potentially semi-stable. Okay, and but in that case, the potentially semi-stable case is just a semi-stable representation twist a character, and then so after chi prime, so you can see that. Okay, for the total, sorry.
In all these elements, V is supposed to be 1, 2.
Oh, one of the row I, yeah.
For which you have the information.
Yes, that's a local proof.
You know that the tensor product is good, I suppose.
Yeah, you know the tensor product is good. Okay. And then you tensor chi, so the one hot tit weight is integer.
But already your first step is an analog, I suppose, known of the Denominator theorem, right?
Yeah, I just try to explain this idea, and then I will extend the idea of this theorem. So if you know that one character to make this representation have one hot tit integer, then pretty much everything will follow up. But on the totally real case, in the global case, it's kind of very hard to do that. But it turns out to finally see that, okay, you can think about the determinant. This is the global character because V is just a global representation. And somehow you can, if you can take a square root about that, so then you can do the very similar job to prove that. So it's not quite hard. So, all right. So finally, for the theorem 2, it will be nice to if it can be applied to a compatible system. But in such case, you see, you need to know for certain kind of representation, the reduction of that representation is absolutely irreducible. So in the theorem, one proposition of the paper BGGT I mentioned there have a proposition to say that if you given compatible family, so there will be have a prime of identity 1 such that you can always select the representation such that the reduction is absolutely irreducible. Okay, so but that as usual is required to some a regular condition. It seems that the regular condition, it looks like the regular condition if you consider the situation that 0m m2m. It's still okay, but I shouldn't say claim that it only looks okay, but I was still reading that proof of the proposition to see if it can work through. Okay, I stop here.